All right, everyone. Welcome to another episode of the TWiML AI podcast. I'm your host, Sam Charrington, and today I'm joined by Bayan Bruss, Senior Director of Applied ML Research at Capital One. Bayan, welcome to the podcast.
Thanks, Sam. It's great to be here.
It's great to have you on the show. I'm looking forward to digging into our conversation. We'll be talking about some of your work on deep learning for tabular data. But before we get to that subject, or to get us to that subject, I'd love to have you share a little bit about your background and how you came to work in the field.
Sure, happy to. Really excited to be here. I love this podcast, by the way. I've learned a tremendous amount over the years. In my current role, I lead applied machine learning research at Capital One. Capital One, of course, is a major financial institution in the United States and Canada and the UK. And we provide a broad range of financial services products to consumers. And within that, we use machine learning for a number of our applications in how we provide those services to our customers. And it's really embedded across the ecosystem, across the business. And we stood up several years ago a team of applied machine learning researchers, which I lead, with the goal of looking at the field of machine learning. And as we know, and as you've brought on many guests, the field itself is advancing quite rapidly. There's a major breakthrough, it feels like, every 6 months. And so the idea behind applied research was, okay, what of that realm of all possible advancements is it all relevant to us as a financial services institution? How do we distill that down into something that is useful for the kinds of problems that we try to solve as a company? And then, once you've kind of narrowed the focus a little bit, narrow it even further by saying, which of those techniques, which of those breakthroughs actually work on our data, which of them actually work for specific use cases and problems within the company. And that's a hard problem, because a lot of the data that gets used in many of the publications that's out there, a lot of the benchmark data is very pristine. It's very static. It's used for time and time again in a variety of different experiments, and so it's been picked over by a number of different researchers. When you compare that to the kind of data that we use inside the company, it's messy, it's noisy, it's complicated. You may only have a few people that have really rolled up their sleeves and worked with it for a number of years. And so there's a big gap then between the breakthrough and then what actually works when you try it out on the noisy, messy data. So our team's goal then is to narrow the scope down, figure out what actually works, test it on our use cases, and then take it a step further. Can we actually generalize that, build it into some of our production systems and tools and platforms, and make it available for data scientists across the company to then use it in a variety of our use cases? And so the ultimate objective is to shrink the time from when something's discovered or some innovation or some breakthrough is made to when it can be used in servicing our customers in a unique way. And so that's kind of the mandate of my team. I've been with Capital One for 5 years now doing that. Before Capital One, I had a mixture of background in academia and startups and consulting. And when we look at the areas that we could be focused on, I mean, there's obviously quite a lot of uh, the space of machine learning is fairly massive. So we tend
Just fairly.
it's just fairly. I mean, you can hardly read everything if you spent all your time just reading all the papers that were out there. But we try to organize ourselves thematically around topic areas within machine learning, and then that changes over time depending on whether there's something some new advancement that's really exciting, and we're like, okay, we need to really focus on this. But they at the moment, what they are for us is we have a very strong interest in graph machine learning as a company. As a financial services company, we basically work with data that is derived from financial networks. Right? When you swipe a credit card, you are establishing an edge between yourself and a merchant. And so every time our customers process a payment, they are doing so on a network, a financial network at a national, global scale. And so that network then becomes quite useful in a lot of our applications if you can have machine learning that can handle the kind of cardinality and sparsity that comes with that kind of network. And so we've been working for a number of years on taking a lot of the advancements that we've seen in graph convolutional networks and even other more traditional graph mining algorithms and applying them to some of our financial services applications. So that's one of the topic areas that's kind of been a long time for us and continues to be of high interest. Another one is explainability and interpretability. As a uh, highly regulated financial institution, we have a very high bar for understanding the soundness of our models, understanding the way that our models are making decisions. And so, as we use more machine learning across the company, we've thought it very important to invest in figuring out of all the advancements in model explainability and interpretability, which ones can be most useful in helping us manage our risks and manage the way we deploy models as a company better. A third one is anomaly detection. Financial services, we are, kind of under attack from fraudsters on a daily basis. Those attacks are extremely creative. We have a lot of different ways of defending against those attacks. Some of those include supervised machine learning, where we've built these massive models that look at all of our credit card transaction data and can predict with fairly high accuracy whether a given transaction is fraudulent or not. Sometimes they're rule-based systems, a combination of both of these in heuristics. But in addition to that, we realize that there's a broad range of anomaly detection algorithms and advancements, particularly as you start to look at how do you scale anomaly detection to the kinds of scale that we're working with, that would allow us to capture emerging trends of fraudulent behavior or other kinds of nefarious behavior that might be escaping what a supervised model has seen in the past, right? Your supervised models can only generalize based on what they know. And if it's a new attack pattern, you have to have something that is not conditioned on that distribution in order to capture it and respond to it effectively. And so that's where we see the promise in anomaly detection. And then the final area that we're actively focused on, kind of internally focused, is around privacy. We've worked for a number of years in how do you generate synthetic data so that you
Okay.
can provide people with an understanding of the data that might be in production without actually giving them access to that data. Um, we have more recently started to explore federated learning as a domain where we could potentially train models at the edge. Um, Now, beyond those four areas, which kind of are very like pressing and we're focused on at the moment, there's also some areas that we're looking out into the future and saying, okay, this could be a potential game changer. And oftentimes, when we're looking at those areas, we partner with major academic institutions to help us flesh out the ideas, help do some of the more experimental research, publish papers, engage with the community. It has a couple of really nice benefits. One is that if it's an area that's underexplored in the research community, by funding it and getting a community of researchers, it kind of has these like cascading effects where more researchers say, oh, that's actually an interesting topic. Let's do some more research. And then you fund one thing and three more papers come out from others on the topic because it's become something of interest to the community. And so, within that realm, and what we were going to talk about today is this domain of deep learning for tabular data. Tabular data, as we look to our use cases as a financial services company, many of our data problems are formulated within this realm of tabular data. So, and for those who don't know, tabular data is essentially structured data, is another term for it. It's a data that comes in a table as opposed to an image, which you have a grid or text where you have a sequence. Tabular data is, you can think of it as this mixed type data set where you have some numerical features, some categorical features, some discrete integers, and usually they're like compiled from a variety of source systems into a single snapshot of the population you're trying to build a model on top of, and then you build and train a machine learning model to make some kind of prediction.
You mentioned earlier kind of this flood of innovation that's been happening in the field. A lot of the flashiest innovations in machine learning have been focused on images and NLP, to name a couple of examples, graphs as well.
Yeah.
Um, there's been a bit of work on tabular data, but it doesn't seem like nearly as much, especially considering its prevalence in the broader industry, right? Banks run on tabular data, most businesses run on tabular data. Any takes on why that is?
I think there's a couple reasons, and it really boils down to the quality of the baselines. I think if you look back 2 decades ago, the quality of the baselines in language, and then not to disparage the language researchers from 20 years ago, like they just weren't that great. Or computer vision, they, you know, the room for growth was humongous. And so then, when you're starting at a very low performing model and you can see every year exponential improvement, well, that gets everybody excited, and more research and funding goes towards that. Whereas if we look at uh, the evolution of machine learning for tabular data, you start with very simple linear and logistic models, and then you kind of advance into your support vector machines, and then you see these non-parametric tree-based models and ensembles of tree-based models like random forests and gradient boosted machines. um, those have They do really well, and it's hard to beat them. And there's another piece to it, which is that not only do they do well on a wide variety of problems, and the tooling ecosystem that's been built around them, tools like XGBoost and the whole ecosystem of Python for data science has really exploded in the last decade, make it really really easy to use those techniques. And so there's not a whole lot of incentive to ask, okay, well, what's outside of that paradigm? Um, and I think there's a third factor in it, and that's primarily that like a lot of the big public benchmark data sets are in computer vision and in NLP. There hasn't historically existed kind of these big challenge type data sets for tabular data where you can see that benchmark improvement year over year at some of the big conferences like CVPR. And that's the other piece that's missing, I think, from the field. I think the biggest one is the fact that they're really good models. But what you've seen as a result of that is, as you said, like all of this research has focused on computer vision, NLP, and more recently graphs, leaving a huge application space of tabular models outside of the main line of machine learning research. Still a ton of research that happens in the statistical literature, but the kind of the stuff you see at ICLR and NeurIPS and ICML hasn't primarily focused on tabular data for the last few years, with some research here and there. But a couple of things that are interesting. One is that we haven't fully explored how the advances that we see in computer vision and NLP apply to tabular data. I think historically we would have said, oh, there's no relationship, right? It's a completely different domain. There's no way to reuse those components. That was actually originally said between computer vision and NLP, right? Like there was this big,
Right.
you couldn't use language models for vision and vice versa. And then more recently, we've
Now
seen
look where
that,
we are.
yeah, exactly.
Yeah.
Transformers can be used for everything. You can also, certain instances of language can be modeled quite well with, image data, image models. And so I think the same thing could be said for tabular data. It's just a matter of asking the questions and doing the research and doing the exploration. The other piece that is really really critical is that all of the research that surrounds uh, computer vision and NLP models, primarily around answering questions of how do we make these models robust? How do we make these models interpretable and explainable? All of those are often predicated on the model itself being a deep learning model, right? Many of these techniques require a differentiable model. And so, in a lot of cases, we can't take those techniques and then apply them to your XGBoost model. You've created this bifurcation in what is possible if you use a neural network and what is possible if you don't. And by maybe closing that gap and asking, can we do the tabular data in the same paradigm as we're using for computer vision and NLP? Can we then take all of that, you know, um, support that's been built around those deep learning models in computer vision and NLP and use them for our tabular data. And so that's one of the exciting things about bridging the gap between the two fields. I think, like, candidly, because the baselines are so strong in for methods like, gradient boosted trees and random forests, it's that ecosystem of functionality that makes it compelling more than, incremental improvements, marginal gains in the overall performance. I mean, everybody gets excited when you have a table where you're performing the best on all the data sets you're testing on. But from a practitioner's perspective, it's much more exciting to be able to use, the broad suite of capabilities that come with deep learning.
I'm curious, are there specific things that come to mind there? I generally get the idea of, hey, we've got, this broad set of tooling that, has been built up around deep learning. And some of that I can see, for example, hey, you use TensorFlow or PyTorch, you want to use the same tool chain for everything just for efficiencies and, learning curves, all that kind of stuff. But some of the other things, I'm not sure if you specifically mentioned, like some of the explainability methods that are based around deep learning do um, kind of strike a little bit of, hey, we've got these tools to solve these problems that were created by the methods that we're using to solve problems that, we can solve otherwise with better performance that don't have the same opacity.
Yeah, that's a good point. They Many of these tools were developed to, as you say, solve some of the problems that come with deep learning. However, uh, many of the models that you will find used in large industrial systems will be equally opaque. There's it's just as hard to interpret or understand a tree-based model that has 10 splits per tree, and that has several thousand trees, and that has several thousand features that's being used. It's equally hard to explain a single decision of that type of model as it is to explain a neural network. It's no less complex a model. It's not capturing any fewer interactions. It's just modeling the data in a different way. And so I think we're seeing a growth in complexity of machine learning models, regardless of what you're using, whether it's a deep learning model um, or a tree-based model. But I think what we're seeing is that for deep learning, it, there's just been this huge investment in trying to understand how they work, because I think maybe partially because they've been so effective and people want to know why. They want to know what they're learning. As we start to make claims about uh, intelligence, people want to pinpoint factors in the decisioning of these systems, and so that spurred all of this research. It's available, it just doesn't work for these other tools that we use. But I think that it's really, really, I mean, it's important not to just say, like, oh, because it's good for deep learning, it'll work for these other systems. But there are certain problems that we've been able to see um, the methods that were developed for deep learning to be fairly powerful for tabular data. If particularly in the realm of explainability, and I'll give you an example. There's a subdomain of model explanations, local explanations, called counterfactual explanations. I don't know if you're familiar with counterfactual explanations. Sure, a counterfactual explanation essentially is asking the question, for a given input to a model, what would have had to have been different about this input in order for the model to have made a different prediction? And so you think about a binary classification task, whether or not a credit card transaction is fraudulent. Well, we can say, okay, given that this transaction was classified fraudulent by this model, what would have been different about that transaction for this model to not have thought that it was fraudulent? So, what feature changes would you need? And those feature changes, the difference between the actual features and what would have had to have been different, becomes the explanation of why that model made a decision. And there's a lot of different ways you can do this, and there's been you know many papers on the different techniques to do this. A very, very simple way to do this is to take the inputs to your model and project them into a lower dimensional space, and then search within that lower dimensional space, which is now a continuous space, right? This is the standard way that a neural network works. The shortest path to another data point where the prediction is different, and then come back out from that lower dimensional space using like a decoder to original feature space. And now you have input to a model in the original feature space that, if you had used the original model to predict it, would have resulted in a different classification. Now, in order to do that, you need a differentiable model. You need to have the ability to train a model such that it can project into that lower dimensional space and use the gradients with respect to the model prediction in order to do that. There are other ways to solve that problem. There are ways that don't require you to use the differentiable model in order to come up with the counterfactual, but that's a very simple and very efficient way to do it. And if you had a deep learning model, you would be able to do that. So that's an example where there are solutions out there. You don't have to use deep learning, but a lot of the paradigm makes it a lot simpler once you adopt it. Mm-hmm. I do. I think that's one of the really exciting things is this, uh, deep learning is compositional, right? You can take pieces of deep learning systems and build them together and then train them in an end-to-end fashion. Multi-modality allows us to do that in ways that we would never be able to do, or we would have to do in very, very complex ways historically. A good example of that would be within the domain of graph machine learning. So we have these complex financial networks. We want to build models that help us predict individual entities, status within that network. Those individual nodes will often have a lot of tabular data associated with them, in addition to the edges that connect them on the graph. And so knowing what the right way to encode that tabular data is and how to build that into a broader differentiable model, a deep learning model on the entirety of the graph, it becomes really, really powerful. And I think the things that are most exciting that we're all getting very excited about, things like DALI and stable diffusion, are situations where people have figured out how do we fuse together different domains of data in ways that allow us to interact with that data in entirely new ways. And quite frankly, I'm not entirely certain all the different ways we're going to be able to use multimodality within financial services. But I think once we've proven how you can do it, we're going to see a lot of really exciting applications come out of that. Yeah. I think fundamentally the data is different. The data tends to come from the process that generates the data is usually not actually a single process. Oftentimes in tabular domains, it's multiple processes. You might be looking at some combination of uh, customers' payment history, along with information about where they spend their money. And so those are two completely different systems. They're not actually fundamentally related in any other way other than they're with regards to a specific customer. You take those data sets, you engineer the features, you combine them together, and now you have a tabular data set. Unlike an image where you have this continuous distribution, at least within a specific domain, all the images come from the same distribution. They are fairly well structured in the fact that there's strong local correlations within an image. Nearby pixels are very highly likely to be similar to the one next to them. Columns in a data set have no inherent structure to them. There's nothing other than the peculiarities of the data scientist who put that column next to the other column that determined their proximity to one another. So a lot of that inherent structure is missing, which is one of the reasons why transformers are starting to be the thing that's bridging that gap, because transformers can look across the entirety of the data set and determine what context is important. They don't have to rely on individual proximities that are hard coded into the architecture to figure that out. So that's one, is the mixed type and the lack of inherent structure. I think there's been some really interesting work, and it's primarily been focused on not necessarily architecturally how do we handle tabular data, but it's focused on even a level before that, which is how do we encode the data in a way that a deep learning model can utilize that information more effectively. And so a number of researchers have started to point out that varying encoding schemes have a tremendous impact on the quality of a deep learning model for tabular data. And so these encoding schemes can be anything from simple linear projections. Yeah, exactly, piecewise linear projections, binning, etc. Um, all of those have a very strong effect. Another, uh, so I think there's going to be more research just into how do we encode data better. I would also be very curious, and I don't know if anybody's done this yet, if those encoding strategies also benefit models like XGBoost and random forest models. It might be that rather than doing simple one-hot encoding, like some of these more complex encoding, both for numerical and categorical features, benefits all models, and that would be great. Another thing that's been really profound, and some of the researchers that have pointed this out, I think, are doing great work, is that the way that you regularize the model has a profound impact. And that's not surprising. Regularization kind of rules everything in machine learning, and that goes back to computer vision, NLP as well. And interestingly enough, if you go back and look at the original research on like XGBoost, one of the key things they introduced in that model was novel ways of regularizing the decision trees. And so regularization is kind of one of those foundation steps that if you're ever going to walk into a new domain of machine learning, you have to figure out what regularization works for this particular domain. And there was a paper a while ago that just found that if you did hyperparameter search over a group of possible regularization techniques for any given model, and you selected the optimal subset of regularization techniques, very simple models like MLPs could perform outstanding on tabular data. It was just they called it a cocktail of regularization techniques. And, I think that's a really interesting approach. Interestingly, they also included in what they're calling regularizing a variety of data augmentation methodologies. Uh, this is an area where NLP and more recently computer vision have seen really interesting research, which is how do we augment the data and use it for self-supervised pre-training in a way that makes our downstream models more robust. And that is, this data augmentation is an area that is almost completely lacking in the tabular data domain. We don't know what works exactly. Synthetic data, yeah, but we don't know what the right techniques are. I mean, I think, something like cut mix might work well on an image, but do you just apply cut mix to a tabular data set? Now you have to define a scheme of data augmentation that actually makes sense for this mixed type domain in tabular data. And so I think that's an area that's really interesting. There's a final area. So we have encoding, we have regularization, and then there's finally architecture. What architecture really impacts? And we've been looking at this for a while now, and we've been partnering with Tom Goldstein at University of Maryland. His grad student Gautami Samapelli wrote a paper a few years ago called Saint that looked to take a lot of what we've learned in transformer architectures and apply them to tabular data. And this was one of the first papers in this area, and kicked off a lot of the subsequent research. And kind of the novelty of that research was twofold. One was, one of the first papers to look at transformer architecture across a row within a given data set. So the goal of a model like that is to ask for all of the features that I'm using to predict this particular outcome, attend to the ones that matter the most for this particular goal. And that seems fairly straightforward. Transformer architectures are designed to do that. Uh, Interestingly, Saint also uses this notion of intersample attention. And so it takes subsamples of the training data and it asks not just to attend to the individual row that is for a specific data point, but of all the other data points in that sample, which one is most useful to this prediction task? And so it almost brings together uh, a transformer architecture with like a k nearest neighbor classifier. So you're not just attending to data points that I'm interested in, you're also attending to similar data points or maybe even dissimilar data points depending on what's most useful to the task at hand. And Saint was a very foundational paper in the space. Since then, there's been a number of different transformer papers that have looked at how do we apply these architectures. Uh, as I mentioned, some people have pointed out that given good encodings and and good regularization, maybe you don't need a transformer. I think the question of architecture is still an open question, as much as the question of regularization and encoding is an open question. But I I ultimately think that the combination of these three in whatever the final state will be a powerful new tool system for deep learning on tabular data.
And so, where are we? Like, does how far does Saint get us, or how close does Saint get us to solving the problem? Is it just kind of demonstrating a particular, a direction?
That's a good question. It far depends on the journey that you're on. Um, I think if right, like it all depends on the end destination. If you look at some of the recent survey papers on the field, what they found is that on small data sets, anywhere from 0 to 50,000 training samples, it's hard to beat a well-trained XGBoost model tuned hyperparameters. Like that still is the dominant paradigm. You start to see some of these deep learning methods exceed that when you get above 50,000. And so I think for a while, we're going to see a gap between small data sets and large data sets, much in the way that for many years we saw within the field of NLP. If you're working with a small data set, uh, for instance, for sentiment analysis, it was much more effective to do a TF-IDF encoding and a logistic regression model than it was to use a big language model if you only had 10,000 training samples. I think we're in that paradigm. Where NLP eventually went was if you had a large language model that was trained in an unsupervised way, you could use it on small data sets and fine tune it quite effectively. So maybe we'll get there with tabular data. Maybe there will be this notion of, large pre-trained tabular data models that can then be used on small data sets and effectively transfer their encoding.
What does that actually mean? Like, what is the underlying the underlying relationship between all tabular data that such a thing would exploit?
Yeah, that's a great question. We're starting to make progress on that. I don't have an answer to your specific question, but we're starting to make progress. Very simply, we recently submitted a paper with Roman Levin and also Tom Goldstein, Micah Goldblum, Andrew Gordon Wilson at NYU, and a number of other grad students, where we're looking at transfer learning within the realm of tabular data. And the idea there is if you have a high level of overlap between the feature space of any given task. So in that case, we're looking at medical prediction. So we have uh, a variety of tabular data sets. A lot of them contain a lot of the similar features, and some of them contain distinct features. They're all trying to predict different diseases. Um, and um, and so the idea was, can you pre-train a tabular data set on, maybe one of the larger data sets and the predictions for that given disease, and then transfer that. Maybe the feature set is slightly different, and we had to come up with a novel way of how do you, uh, you know, adjust the feature set within this pre-training scheme. But then, can you use the learning from that much larger data set into that smaller one? Now, again, that is very different than a foundation model, which basically gobbles up all of the language on the internet, pre-trains, and then can be used for anything. That
Right.
is transfer learning in a much smaller scope. But I think it's a starting point to say that yes, you can use a generic feature encoder from a tabular data set and extend it to other tasks in a way that retains the original structures that you've learned. I do think that we would have to answer the fundamental question which you asked, which I think uh, is still not clear in my head, which is what does it mean if you were to go and build a, a model that included every tabular data set in the world? Like, what would it mean for a combination of a healthcare data set with a financial services data set with like a wine classification data set? I mean, we've seen all of the data sets that are out there. They're fundamentally different. So what is it learning?
Now, on the other hand, maybe kind of rolling back a little bit of my disbelief, I think we're interested in tabular data because tabular data is kind of this fundamental currency of business. Like it's all over the place, but I suspect that there's a lot of the same thing happening in lots of places. Like there are a lot of churn models, like there are a lot of fraud models, like there's you can I don't know how many kind of super classes, if we were to try to taxonomize, all of the tabular data sets, what that looks like. But, if you could get access to a whole bunch of, churn, you know, data sets that related to churn models, I could envision like some kind of foundational churn model that understands propensities to do something based on other things.
I,
I don't know.
I think that's right. I think that's right. Even if the inputs are fairly heterogeneous, I think that is, and luckily within industry, there's not there are not very many companies that like span multiple distinct domains where they're trying to predict credit card fraud and disease outcomes at the same time. Like you don't see that kind of conglomeration. So yes, within an individual companies, this notion of transfer learning or even kind of industry specific foundation models actually do potentially make sense. Globally across all data sets, that's maybe a little bit uh, extreme, but yeah, I think within specific domains, specific applications, we could certainly think about how you bring together all those different types of data sets and tasks into a single modeling framework.
Of course, the task of pulling those data sets together is a very different one from collecting images or text off of the internet.
Yeah, it's not as easy as just like
Meaning just the
scraping.
political,
Yeah,
the access to the data itself.
That's right. And many tabular data sets, because they are collected within company walls, are actually quite sensitive. They contain private customer information that, rightly so, those companies don't want to share publicly and make available. Um, Very little exists the way that text and images just exist free to grab on the internet within the domain of tabular data sets. But within specific industries, there might be some consortiums that emerge to, start to bring together uh, groupings of those types of data sets. If this paradigm seems to be the one that people find promising, certainly, I think, when we look internally at some of these, as you said, you're whether it's churn or it's marketing or fraud detection, a lot of times you're using either similar overlapping data sets and variations on a theme when you're talking about your task. And traditional industry would build a separate model for each one of those use cases. And when you're first getting started as a company in machine learning, having a separate model for every single thing is probably not that big of a deal. You've got 10, 15, 20 models that you're maintaining. When you become a full-fledged adopter of machine learning and you have hundreds of models that you're running in production, and they're interacting with each other in ways that you didn't anticipate, and they're relying on each other in stacked ways, managing that overall system complexity becomes really, really critical and a very big challenge. And so rethinking it as a single pre-trained model with a lot of smaller fine tuning, that actually changes how you do business. That changes the tech stack that you work with. That changes how you think about the overall machine learning ecosystem. And so I do think, like, long term, it could potentially help a lot of companies reduce their overall machine learning complexity if they think about it that way.
What do we know about solving tabular data problems? How do you, what's most important there? Um, and how do you think about approaching them today for the real problems that you're trying to solve today?
Yeah, I think that the biggest gap right now that's standing there between some of this research that we've been talking about in deep learning for tabular data and what we would actually use internally is not necessarily kind of at this point a novel architecture or a novel encoding scheme or novel regularization technique. I think each of those has more research, and there's going to be some more work that figures out, like, which is the best or which are the sets of best. I think the biggest gap is tooling. Is, do we have tools that are as easy to use as scikit-learn or XGBoost, that you can fit and deploy a tabular data model using using deep learning as you can for tree-based methodologies. And when I say easy to use, it's you know everything from not having to configure 1,000 hyperparameters just to figure out which one's going to work best, to, is it hardened and uh, you know well documented? Does it have good logging? Like, the whole software engineering side of it is actually, I think, what's missing at the moment. There's been a lot of great research, but now there just needs to be some really good quality engineering that takes that and figures out, okay, can we build libraries or packages that make this so that it's not a data scientist figuring out how to apply research, it's a data scientist using a tool, right? Like, that's the gap,
That
is
sounds
that
like a
the data scientist.
fairly well stated problem, and I know Capital One loves open source. Like, is that, are you working on that?
Yeah, that is that's a well stated problem, because it's something that we're thinking about and working on. Yes, but I do think that's the biggest gap at the moment.
Maybe this is a tangent, but you mentioned graph learning, deep learning on graphs, that whole direction. Um, do you think that that plays into working with tabular data in a big way? Like, is each of the rows in a tabular data set kind of a node in a graph, and that's going to help us figure all this out?
Yeah, that's a really interesting question, and I think one that's not well studied enough. I mentioned in Saint how uh, the Saint architecture takes a transformer and applies it to each of the rows. And then it takes that same transformer and looks uh, across rows in a subsample of the data. It, if you think about what that's doing, is it's essentially treating the data set like a similarity graph. It's saying, okay, I've got all these data points. Each one of them is a node in this data set, or at least within the sample of it. Attend to the neighborhood around me that is most useful for this task. And so it transforms it into a graph. But I don't think, even when we worked on the paper, we didn't really dive into that element of it and looked at the connection between okay, now that you've structured it as a graph, or you're even thinking about it as a graph, how does that change how you approach the learning task? um, I definitely think this question of how do we create graphs from tabular data is an important one. As we look to uh, leverage more graph machine learning, there is a big question of how do we take, and it's not always tabular in the sense of like features in a model. Sometimes it's just tabular data of records about a customer that we want to build into an actual network. But there's a fundamental challenge in how do you go from that structure of a data table into something that you can use, a graph convolutional network, or even something simpler like belief propagation. It's a really hard problem oftentimes to go from data tables into graphs. And I think that's one that we're actively looking at the moment.
Where would you say the kind of research frontier is and is kind of heading around this problem, deep learning for tabular data?
I think, one we mentioned, which is self-supervised pre-training. What are the, you
Transformers
know,
and so yeah.
and particularly, what is the right way to augment data going into that? What's the right way to um, build kind of transformer backbones for tabular data? Um, I think there's going to be continued study on encoders and regularizers and how you do the optimal combination of those. I don't think that's going away. Um, and then I think from a theory perspective, we have to understand a little bit more about, particularly as you start to combine data sets and as those data sets get more and more heterogeneous, what exactly the architecture is doing in that domain that it makes it at all useful for any of the downstream tasks. So as we start to push into larger pre-training, maybe this idea of foundation models for tabular data, um, there's open questions, not just on how do you do it, but like what does it even mean, and why would you do it? Because I think most people, if you mention that to them, will have a very similar response to the one you did, which is, why would you even do that? That doesn't make any sense for tabular data. And I think that's a very reasonable response. It doesn't make any sense. And so if we're going to do that research, which I do believe we will, and we have to, because that's the direction of that we're seeing many of the domains of machine learning research go, we need to answer that question.
And what does doing that research mean? Is it just collecting more and more and more data sets and seeing what happens when we try to train models on them?
Yeah, collecting more and more data sets, seeing what happens when we try to train models on them, understanding how to combine those data sets, how to train uh, across multiple domains. Whether, I mean, we talked about multi-modality, but even how do you build a transformer architecture that can then take in a variety of different tabular data sets? Some might combine a bunch of categorical features. Some might be very, very small data sets. Other might be very large data sets. The scale and complexity of the diversity within the tabular domain is much greater than it is in computer vision NLP. And so those are the kinds of questions we have to answer: is how do we build things that can generalize using all of that diverse data?
Yeah, so we kind of set this up in talking about there are all these benefits that you get from the deep learning ecosystem and tooling. The disadvantage is that we're not kind of at performance parity with the established methods, XGBoost and the like. But you've also kind of highlighted that there are key gaps in terms of the tooling. Um, Do you need to get to performance parity in order for the benefits of the deep learning ecosystem to um,
I actually think that we are already at performance parity. If you look at a lot of the research, many of these models are performing as well, sometimes worse, sometimes better, but on average as well as XGBoost. And so that's why I was suggesting that it's the tooling ecosystem that needs to improve. I think, many data scientists love the benefit of well-defined APIs like scikit-learn and XGBoost, and that they they don't have to spend a lot of time thinking about how do I get this piece of software to work for me. They just know that the piece of software has a fit function and a predict function, and maybe 6 or 7 hyperparameters that they have to know about, and they have to know what those 6 or 7 hyperparameters do with respect to how well that model operates. Many data scientists aren't used to, particularly ones who aren't working on computer vision and NLP, having to answer 400 different questions around whether I use this particular type of encoder, whether I use these sets of regularizers, how deep does it need to be, what are the dimensions of each of my different encoding transformer encoders, etc. There's so many choices in deep learning.
uh,
It
yeah.
makes it really really hard to plug and play the way that you can plug and play with like uh, uh, an XGBoost model or a random forest. And so I think as we start to learn what things work the best, we'll get to a place within the deep learning tabular data ecosystem in which there are some tools, they have very simple APIs, and a lot of that decision making has already been made in the way that the tool has been built. And it reduces the complexity and the decisions that the data scientist has to make when they're choosing to use that model. And I think that's when we'll finally see widespread adoption. And once that's in place, then all of the other stuff like the explainability, the ability to quantify uncertainty, all of the things that have been developed around deep learning will start to be added on top of that. But that very simple interface, that very simple API, I think is the major hurdle that a lot of people face when they try to start using deep learning for tabular data. There's just too much for them to figure out.
Well, Bayan, this has been a wonderful chat. It's been a while since I've had a guest on the show talking about the topic, surprising as important as it is. But this has been a great chat to get caught up on it.
Thank you so much. It was an absolute pleasure. I really enjoyed talking to you today, Sam.
My pleasure. Thank you.